The activation energy of iodoacetone synthesis
By Damian Barrios.
and Jeong.
So let's start this all off with what the iodoacetone reaction is in the first place. So here's the full balanced equation. Although I'm not sure you recognize everything here, I'm sure we can get through it eventually. On the left over here, we have acetone present in an aqueous solution, iodine also present in aqueous solution, and we have hydrochloric acid as our catalyst for the reaction. Here we have the star, iodoacetone, the byproduct, hydroiodic acid, and hydrochloric acid as the catalyst, completely unchanged.
So first, we gathered 30 milliliters of 4 molar acetone, 1 molar hydrochloric acid, DI water, and iodine dissolved in water. We then measured 2 milliliters of all the reactants except iodine and added to an Erlenmeyer flask. We then add 2 milliliters of an iodine solution to a test tube. We then placed the Erlenmeyer flask and the test tube in a 1-liter beaker filled with water and measure the temperature. We leave it to equalize temperature for about 5 minutes. Then we add the iodine to the Erlenmeyer flask and then swirl it and place it back in the bath. We then measure how long it takes for the solution to become clear. And we repeat this trial at many different temperatures between 5 degrees Celsius and 20 degrees Celsius. We will determine K, the rate constant, given that the reaction is first order with respect to acetone and hydrochloric acid. We will graph the natural log of the rate constant and the inverse temperature of Kelvin and recover the slope of a linear line of best fit. Finally, we will multiply the slope by the ideal gas constant.
So let's start this off, or I guess follow up with the apparatus that we used to complete this experiment. As you can see by my absolutely perfect drawing, you have a 1-liter beaker that's much bigger than the liter, a thermometer, an Erlenmeyer flask, and a test tube. Now here's an actual picture, which surpasses my drawing in every way, where you can see the test tube with the iodine solution. You can see that nice yellow shade just underneath the water where my mouse is. The Erlenmeyer flask, also sitting in there, has all the other reactants in it, nice and clear, hard to see. And a 1-liter beaker filled with water to maintain temperature. And the thermometer isn't here, but normally it is. And as you can see through the 2 videos we have here, when you added the iodine in originally, solution was nice and yellow. As the reaction continues, it becomes clear and very apparent that it is clear. Now up here we have all of the data from the experiment. We've got our 7 runs, temperature recorded in Celsius, and the reaction times measured in minutes, seconds, and then milliseconds.
So some quick calculations. For the rate of the reaction, we got 3 times 10 to the negative 4. And we divided the rate of the reaction by 1 molar acetone and 0.25 molar hydrochloric acid to get the rate constant. Then we got the natural log of the rate constant and made it the y-axis of the graph. And we converted to Kelvin for temperature. Then we inversed it and made it the x-axis for the graph.
So as for what the graph visually looks like, we have, well, here's our graph. It goes from a maximum value of about 10.7, or negative 10.7, to a minimum value of around negative 12. As you can see here, not exactly the most accurate experiment given the r-squared of 0.62, but we do the best with what we have. And the important part here being negative 6,228.
Some quick calculations again. So we need to make this negative 6,200 because we need 2 significant figures. And in order to get the activation energy, we will multiply it by negative to make it a positive and multiply it by 8.134 joules. The activation energy is 52 kilojoules.
So thank you for watching our presentation, and
that's all, folks.
of course, credit to Warner Brothers for the outro.